Now, let's talk about Chapter 11, Scaling Inference Pipelines, from Theory to Practice. Turning our attention to theoretical foundations. The operationalization of AI agents represents a paradigm shift from monolithic, static application architectures to dynamic, distributed systems capable of intelligent decision-making at scale. In the context of cloud-native microservices, an AI agent is not merely a model inference endpoint, it is a discrete, autonomous unit of business logic that encapsulates reasoning, state management, and tool usage. Containerizing these agents and scaling their inference capabilities introduces unique challenges that differ significantly from traditional stateless web services. These challenges stem from the computational intensity of AI models, the latency requirements of real-time inference, and the probabilistic nature of AI outputs. To understand the operational requirements, we must first dissect the anatomy of a containerized AI agent. Unlike a standard microservice that might perform CRUD operations on a database, an AI agent orchestrates complex workflows. It might receive a user prompt, retrieve relevant context from a vector database, invoke a large language model, LLM, for reasoning, parse the response, and then trigger an external API action. This lifecycle demands a runtime environment that is both lightweight, for fast startup, and resource-rich, for GPU acceleration. Moving on to the microservices evolution, from monoliths to agents. In previous chapters, we discussed the decomposition of monolithic applications into microservices, focusing on domain-driven design and API gateways. We established that microservices improve fault isolation and scalability. However, AI agents extend this concept by introducing intelligence at the service boundary. Consider a monolithic e-commerce platform. In Book 1, we might have refactored the order processing module into a dedicated microservice. In Book 7, we elevate this further. The order processing service becomes an order agent. This agent doesn't just process data, it reasons about it. It might analyze customer sentiment in a support ticket or predict inventory shortages based on unstructured text inputs. The transition to agent-based architectures requires a shift in how we view state. Traditional microservices are often designed to be stateless to facilitate horizontal scaling. AI agents, however, often maintain conversation history or task context. This introduces the concept of ephemeral state that exists only for the duration of a specific inference task but is critical for the agent's coherence. Now, let's explore containerization, the standardized unit of deployment. Containerization, specifically using Docker, provides the isolation and portability necessary to run these agents consistently across environments, from a developer's laptop to a multi-node Kubernetes cluster. The shipping container analogy: imagine a global shipping company. In the past, they had to handle loose cargo, boxes, barrels, and crates of varying shapes and sizes. Loading a ship was a logistical nightmare, and goods were often damaged. The invention of the standardized shipping container revolutionized logistics. It didn't matter what was inside, whether it was electronics, textiles, or machinery, the container fit on the same ship, crane, and truck. In cloud-native AI, the loose cargo is the AI model, e.g., a PyTorch.point file, the inference script, Python/C#, the system dependencies, CUDA drivers, and the configuration files. The standardized shipping container is the Docker image. The global logistics network is Kubernetes. By packaging the AI agent into a container, we decouple the application logic from the underlying infrastructure. We can run the same container locally with a CPU-only environment, for debugging, and in production with NVIDIA A100 GPUs, for performance, provided we abstract the hardware access correctly. However, AI containers differ from standard web app containers in two critical ways. 1. Image size. AI models are large. A single ONNX or SafeTensors file can range from 2 GB to 20 GB. This bloats the container image size, slowing down startup times, cold starts, and increasing storage costs. 2. Dependency hell. AI frameworks rely heavily on specific versions of CUDA, CUDNN, and system libraries. A mismatch between the container's OS-level libraries and the host's GPU drivers can cause runtime failures that are difficult to debug. Now, let's talk about optimizing model serving, caching and layering. To mitigate the latency of pulling large images, we employ advanced container layering strategies. Concept: the immutable layer in Docker. Each instruction in a Docker file creates a layer. Layers are cached. If we place the model weights in a lower layer, changes to the application code, upper layers, won't invalidate the cache for the model weights. We begin by defining the base image for our Docker file. Notice at line 4, we're using NVIDIA/CUDA 12.1 runtime Ubuntu 22.04. This is a critical choice for AI agents, especially those leveraging GPU acceleration. This image provides the necessary CUDA drivers and libraries, allowing our .NET application, which might be calling into Python or C++ libraries that use CUDA, to utilize the GPU effectively. Choosing a runtime image, instead of a development image, keeps the container lean, which is a cloud-native best practice for reducing attack surface and improving deployment speed. This forms the immutable base layer of our container image. Next, at line 7, we install system-level dependencies. We're installing Python 3.10 and .NET 8 runtime. The Python 3.10 is included because many advanced AI models, even when integrated into .NET, often rely on Python for specific libraries, like PyTorch, TensorFlow, or Hugging Face transformers, or for preprocessing/post-processing tasks. The .NET 8 runtime is, of course, essential for executing our compiled .NET application. These dependencies form a semi-stable layer. They change less frequently than application code but more often than the base OS. Keeping these in a separate layer ensures that if only our application code changes, Docker's build cache can reuse this layer, speeding up subsequent builds. At line 9, we introduce a crucial optimization for AI agents, copying the model weights early in the Docker file. Observe at line 11, we're copying Mistral 7b v0.1.guf into /app/models/. AI models, especially large language models, LLMs, like Mistral, can be gigabytes in size. By placing this copy command before the application code, we leverage Docker's build cache. If our application code changes, but the model weights remain the same, Docker will reuse this layer and all preceding layers, avoiding the time-consuming process of redownloading or recopying the large model file. This significantly accelerates rebuilds and reduces CI/CD pipeline times, which is vital for agile development of cloud-native AI services. Finally, at line 13, we add the application code itself. We're copying the published .NET application from .bin/release/net 8.0/publish/ to /app/. This layer is the most volatile, as it changes with every code commit. By placing it last, we maximize the benefit of Docker's build cache from the previous, more stable layers. At line 15, workdir/app sets the default directory for subsequent instructions, making it easier to reference files. Lastly, at line 16, entrypimp.net agent.dll defines the command that will be executed when the container starts. This ensures our .NET AI agent application is the primary process, ready to serve requests. This structure promotes efficient container image building, a cornerstone of cloud-native deployments. The Russian doll analogy, think of a Russian Matryoshka doll. The largest, most solid doll, the base OS and model weights, sits inside. Inside that, you have a slightly smaller doll, the runtime environment. Inside that, the smallest doll, the application code, sits right at the core. When you update the application, you only swap the smallest doll. You don't need to repaint or reshape the large outer dolls. This minimizes the work required to deploy a new version. Model caching strategies. In a production cluster, pulling a 10 GB model from a registry every time a pod scales up is inefficient. We utilize node-level caching or init containers. Init containers, these run before the main application container starts. They can download the model from a persistent volume or object storage and place it in a shared empty.dir volume. Once the model is cached on the node, subsequent pods on the same node can reuse it. Shared memory, SHM AI inference often requires passing large tensors between processes. Docker containers have a default /dev/shm size, 64 MB, which is insufficient for LLMs. We must explicitly mount larger shared memory volumes. Now, let's explore scaling inference, the GPU bottleneck. Scaling AI agents is fundamentally different from scaling web servers because of the hardware constraint, the GPU. In a typical web microservice, scaling is trivial. If CPU usage hits 80%, Kubernetes spins up another pod. The new pod handles requests immediately. For AI inference, the heavy lifting is loading the model into GPU memory, VRAM. VRAM is a finite resource. A single NVIDIA A100, 80 GB, might only fit 2 instances of a 30B parameter model. The valet parking analogy, imagine a high-end restaurant with a small parking lot, GPU VRAM, managed by a valet, Kubernetes. Standard web service, cars, requests, are small and easy to park. If the lot is full, the valet calls a rideshare, scales horizontally. It's cheap and fast. AI inference, these are large buses, LLMs. Loading a bus into the parking spot takes time, model loading latency. Once a bus is parked, it takes up 4 to 5 spots, VRAM consumption. You cannot simply call a rideshare because the buses are specialized. You need a system that predicts when buses will arrive and reserve spots accordingly. This is why we cannot rely solely on standard Kubernetes horizontal pod autoscalers, HPA, based on CPU usage. CPU usage is a poor proxy for GPU memory pressure or inference latency. Moving on to Kubernetes native scaling with Kata. To solve the scaling problem, we use Kata, Kubernetes event-driven autoscaling. Kata acts as an advanced metrics adapter that scales applications based on external events and custom metrics, not just CPU/RAM. How Kata works for AI agents. 1. Event source. Kata connects to event sources like RabbitMQ, Kafka, or Azure Service Bus. 2. Scaler. It monitors the queue length, number of pending inference requests. 3. Action. It scales the number of pods, replicas, in a Kubernetes deployment or stateful set. The bank teller analogy. Standard CPU-based scaling is like opening more bank teller windows based on how fast the tellers are breathing, CPU usage. This is inaccurate. A teller might be breathing fast because they are stressed, not because there are customers. Kata-based scaling is like opening windows based on the length of the line, queue depth. If there are 50 people in line, open 5 windows. If the line is empty, close all but one. This is precise and cost-effective. Kata scaled object configuration. Conceptual. We define a scaled object that tells Kata to monitor a specific metric. We begin by defining a Kubernetes custom resource, specifically a scaled object for Kata, Kubernetes event-driven autoscaling. Notice at line 1, API version, kata.sh/v1 alpha 1 specifies the API version for Kata resources. This tells Kubernetes that we are using Kata's custom resource definitions. At line 2, kind, scaled object explicitly declares the type of resource we are creating. This is Kata's primary resource for defining how a workload should scale. Then, lines 3 to 4, metadata.name, AI agent scaler assigns a unique name to this scaled object. This name, AI agent scaler, allows us to reference and manage this specific auto-scaling configuration within our Kubernetes cluster. This setup is fundamental for enabling event-driven auto-scaling for our AI agent microservice. Here, we configure the target for Kata's auto-scaling. At line 6, scale target ref is a crucial field that tells Kata which Kubernetes deployment it needs to scale. Line 7, name, AI agent deployment, specifies that our AI agent scaler will manage the scaling of a deployment named AI agent deployment. This is the actual microservice deployment that hosts our AI agent. Line 8, min replica count, 1, sets the minimum number of replicas. We keep at least one instance running to avoid cold starts. This is vital for AI services, as loading models can be time-consuming, and having an always-on instance ensures responsiveness. Line 9, max replica count, 10, defines the upper limit for replicas. This constraint is often driven by resource availability, such as the number of GPUs in the cluster, or licensing limits for certain software components. This prevents uncontrolled scaling that could exhaust cluster resources or incur excessive costs. This section defines the core of our event-driven auto-scaling logic, the triggers. At line 10, triggers is a list where we specify one or more conditions that will prompt Kata to scale our AI agent deployment. Here, we're using a Prometheus trigger, as indicated by type, Prometheus at line 12. This is a common and powerful choice for cloud-native applications because Prometheus is a de facto standard for monitoring. Lines 13 to 16 define the Prometheus trigger's metadata. Line 14, server address, http://Prometheus server, points Kata to our Prometheus server endpoint. Line 15, metric name, inference_q_length, specifies the exact metric Kata should query from Prometheus. This metric, inference_q_length, represents the backlog of inference requests waiting to be processed by our AI agents. Finally, at line 16, threshold, 10, sets the scaling condition. If the inference_q_length exceeds 10, Kata will initiate a scale-out event, adding more replicas of our AI agent to handle the increased load. This reactive scaling based on real-time workload metrics is a hallmark of efficient cloud-native architectures. Now, let's talk about managing GPU resources, scheduling and isolation. In Kubernetes, GPUs are treated as extended resources. You cannot request half a GPU in the standard scheduler. You request an integer count, e.g., nvidia.com/GPU1. However, modern AI workloads often don't saturate a full GPU, leading to waste. Time slicing and MIG, multi-instance GPU to optimize utilization, we use NVIDIA's MIG technology or time slicing plugins. MIG allows a single physical GPU to be partitioned into isolated virtual GPUs with their own memory and compute cores. This is analogous to partitioning a physical hard drive into multiple logical drives, C, D, E. In Kubernetes, we use the NVIDIA device plugin to expose these partitions as schedulable resources. An AI agent can then request nvidia.com/GPU1, a full GPU, or nvidia.com/mig-1g.10GB1, a slice with 10 GB of memory. The office space analogy: imagine an office building, the GPU. Without MIG, you rent the entire floor, GPU. Even if you only have one employee, AI model, you pay for the whole floor. Other teams cannot use the empty desks. With MIG, the building manager partitions the floor into private offices, GPU instances. You rent a single office, MIG slice, that is secure and has its own resources. Other teams rent other offices. The building is fully utilized. Now, let's talk about efficient model serving, batching and quantization. The final theoretical pillar is the optimization of the inference computation itself. We must distinguish between interactive inference, low latency, single user, and batch inference, high throughput, offline. Dynamic batching: when multiple users send requests to an AI agent, processing them one by one is inefficient because the GPU is underutilized during memory transfers. Dynamic batching aggregates multiple requests into a single batch processed simultaneously. The school bus analogy: if 30 students need to get to school, putting them in 30 separate taxis is expensive and slow, sequential processing. A school bus, batch, picks them all up at once. The bus takes the same amount of fuel to traverse the route regardless of whether it carries 10 or 30 students, within limits. Similarly, a GPU processes a batch of 32 tokens almost as fast as a batch of 1 token, dramatically increasing throughput. Quantization: to fit larger models into limited VRAM or to run faster on less powerful hardware, we use quantization. This reduces the precision of the model's weights, e.g., from 32-bit floating point FP32 to 4-bit integers int4. The photo resolution analogy: imagine a high-resolution photograph, FP32. It captures every nuance of light and shadow but takes up massive storage space and is slow to transmit. A low-resolution JPEG, int4, is smaller and loads instantly. While you lose some fine detail, the main subject remains recognizable. For text generation, the detail, mathematical precision, is often less critical than the semantic meaning, making quantization a highly effective trade-off. Now, let's explore architectural implications and edge cases. Cold start latency: the most critical edge case in AI scaling is the cold start. When Kada scales a deployment from 0 to 1 replica, the pod must start, download the container image, and load the model weights into VRAM. This can take 30 seconds to several minutes. Mitigation: we use pre-warming or sticky sessions. We keep a minimum replica count, min replica count, 1, to ensure capacity is always available. For bursty traffic, we might use predictive scaling based on historical patterns, e.g., scaling up at 9 AM when users typically log in. GPU memory fragmentation: in long-running agents, allocating and deallocating memory for inference requests can lead to fragmentation, causing OOM, out-of-memory, errors even when total free memory seems sufficient. Mitigation: we use memory pools or frameworks like TensorRT that manage memory allocation explicitly. In C#, we must be careful with idisposable patterns and ensure that large tensors are released deterministically using blocks. Dependency on previous concepts: this architecture relies heavily on the dependency injection, DI, patterns established in Book 3. We use DI to inject different inference engines, e.g., iInference engine, into the agent. This allows us to swap a local ONNX runtime for a cloud-based OpenAI client without changing the agent's business logic. The containerization strategy isolates these dependencies, ensuring that the DI configuration matches the runtime environment. Turning our attention to the role of C# in high-performance AI agents. While Python dominates AI research, C# is increasingly vital in production AI systems due to its performance, strong typing, and robust concurrency models. In the context of containerized agents, C# serves as the orchestration layer. 1. Structured concurrency with task T and async/await. AI agents are inherently asynchronous. They wait for network I/O, API calls, disk I/O, model loading, and GPU computation. C#'s async/await pattern allows us to write non-blocking code that is easy to read and maintain. We begin by defining an asynchronous method, generateResponseAsync, which is a common pattern in cloud-native applications. This method is designed to handle a user's prompt and return an inference result. Notice at line 5, the first step involves context retrieval from a_vector store. This is typically an I/O bound operation, meaning it spends a significant amount of time waiting for data from an external source, like a database or a remote vector similarity service. By using await, we ensure that the current thread is not blocked, allowing the web server or agent to process other requests concurrently. This is crucial for maintaining responsiveness and scalability in a microservices architecture, as blocking threads would quickly exhaust the thread pool and degrade performance, especially under high load. Think of it as a waiter taking multiple orders without standing idly by the kitchen for each dish. Moving on to lines 7 to 11, we encounter the core model inference step, which is often the most resource-intensive part of an AI agent. This operation is typically compute-bound, heavily utilizing CPU or, more commonly, GPU resources. At line 9, we call _inference engine.infer async. The comment at line 8 highlights a critical aspect. If the underlying GPU operations don't natively support async/await, we might need a custom awaiter. This is a sophisticated technique to integrate non-async GPU APIs into the C# async model, ensuring that the .NET thread is released while the GPU is busy. This is paramount for cloud-native deployments, as it maximizes the utilization of expensive GPU resources and prevents thread pool starvation. Without this, a single inference request could block a thread for a long duration, severely limiting the agent's concurrency and scalability, especially in a containerized environment where resources are carefully managed. Finally, at lines 12 to 15, we perform post-processing on the tensor returned by the inference engine. This step, handled by _tokenizer.decode async at line 12, is typically CPU-bound. It involves converting the raw numerical output, tensor, from the AI model back into human-readable text. Like the previous steps, this is also an asynchronous operation, ensuring that even CPU-intensive tasks don't block the calling thread. The method concludes by encapsulating the resulting text into an inference result object at line 14. This modular breakdown of the AI pipeline into distinct, asynchronous steps, I/O, compute, CPU, is a hallmark of well-designed cloud-native AI services. It allows for independent optimization, scaling, and even potential offloading of different stages to specialized services or hardware, contributing to a highly efficient, scalable, and resilient AI microservice. This structure ensures that while the GPU is churning on inference, the CPU thread is released to handle other requests, maximizing throughput in a containerized environment with limited CPU cores. 2. Span T and memory T for zero-copy tensor manipulation. Moving data between the CPU and GPU is a major bottleneck. C# provides span T and memory T to work with contiguous memory regions without allocating new objects on the heap. When processing tensor data, arrays of floats, we can use these types to slice and dice data efficiently, reducing garbage collection, GC, pressure. High GC frequency can cause stop-the-world pauses, which are detrimental to real-time inference latency. 3. Dependency injection and configuration. As mentioned, DI is crucial for flexibility. We use the Microsoft extensions.dependency injection library to abstract the inference provider. Here, we're defining an interface named IInferenceProvider. This is a crucial architectural decision. Think of an interface as a contract that specifies a set of methods that a class must implement. In this case, any class that wants to be an inference provider, meaning, it can perform predictions, must provide an implementation for the predictAsync method, which takes a tensor as input and returns a task tensor. This abstraction is fundamental for creating a flexible and swappable AI backend, a core principle in cloud-native microservices. It allows us to change the underlying AI model or service without altering the consuming code, promoting loose coupling. Now, observe the onxProvider class. This class is one concrete implementation of our IInferenceProvider interface. It's designed to handle predictions using a local ONNX, Open Neural Network Exchange, model. This is particularly useful for scenarios where low latency is critical, or when we want to minimize cloud egress costs. Running inference locally within the container leverages the container's allocated CPU/GPU resources directly. This approach aligns with edge computing or scenarios where models are small enough to be efficiently hosted alongside the application. Next, we have the OpenAI Provider class, another concrete implementation of IInferenceProvider. Unlike the onxProvider, this one is designed to offload the actual inference task to a cloud-based service like OpenAI. This choice is often made when the AI model is very large, requires specialized hardware, like powerful GPUs not available in our application's container, or when we want to leverage a managed service for scalability and maintenance. This illustrates a common cloud-native pattern, delegating computationally intensive tasks to specialized external services, allowing our microservice to remain lightweight and focused on its core business logic. Moving on to configure services in startup.cs, we see where the dependency injection, DI, container is configured. This method is the heart of how ASP.NET Core applications manage their dependencies. The iService collection services parameter is where we register our services. The decision to register services here, rather than instantiating them directly, is key for testability, maintainability, and adhering to the inversion of control (IOC) principle. It means our application doesn't know how to create an iInference provider, it just asks the DI container for one. Now, this block is where the real power of our interface and DI setup shines. We are dynamically deciding which iInference provider implementation to use based on an environment variable, useLocalModel. If useLocalModel is true, we register ONCS provider as a singleton. Otherwise, we register OpenAI provider as a singleton. This is a fantastic example of a cloud-native pattern for configuration management and environment-specific deployments. We can deploy the exact same container image to different environments, e.g., development, staging, production, and control its behavior purely through configuration, without rebuilding the image. This pattern allows the same container image to run in different modes, e.g., a lightweight container for development using a small local model, and a heavy GPU container for production using a large cloud model, simply by changing environment variables in the Kubernetes manifest. Let's discuss theoretical foundations. Operationalizing AI agents requires a synthesis of container orchestration, hardware-aware scheduling, and intelligent concurrency. We move beyond simple request-response cycles to manage complex, stateful workflows. By leveraging Kubernetes for orchestration and Kata for event-driven scaling, we treat inference not as a continuous load but as a bursty, queue-based workload. C# provides the robust, high-performance runtime necessary to orchestrate these agents, ensuring type safety and efficient resource management. The ultimate goal is to create a system that is as resilient and scalable as traditional web microservices, while accommodating the unique computational demands of artificial intelligence. Turning our attention to basic code example. Here, we're importing all the necessary namespaces for our application. Notice the Microsoft extensions ones, especially hosting, dependency injection, logging, and configuration. These are foundational for building modern .NET applications, particularly cloud-native ones. They provide the framework for dependency injection, configuration management, logging, and managing background services, all crucial aspects for robust, scalable microservices. Without these, we'd have to manually wire up many components, leading to less maintainable and less adaptable code. We begin by defining our application's namespace, Cloud-Native AI, microservices. This provides logical grouping for our code. Immediately following, we see a comment indicating the core domain models. This is a best practice, clearly separating concerns. For cloud-native microservices, defining these models as data contracts is critical. They represent the API's input and output. The comment also wisely suggests using shared libraries or gRPC/protobuf in production. This is because strict schema enforcement prevents integration issues between services, which is vital in a distributed microservice architecture. Imagine if one service expects a prompt field and another sends text. Without a shared contract, debugging becomes a nightmare. Here, we define inference request as a C# record. Records are immutable by default, which is an excellent choice for data transfer objects, DTOs, in a microservice. Immutability helps prevent unintended side effects, making our service more predictable and easier to reason about, especially in concurrent environments. We're using JSON property name attributes, line 29, to explicitly map C# property names to JSON names. This is important for API compatibility, allowing us to use idiomatic C# naming conventions while exposing a RESTful JSON API that might follow different naming standards, like snake_case. Continuing with inference request, we see properties like request ID, line 33, and timestamp, line 35. Request ID is automatically generated with a GUID, which is a common practice for tracing requests across a distributed system. This is invaluable for debugging and monitoring in a microservice architecture. Imagine a request failing. Without a unique ID, correlating logs from different services becomes incredibly difficult. The parameters dictionary, line 39, allows for flexible, dynamic input to the AI model, accommodating various model types or experimental features without requiring a schema change for every new parameter. This flexibility is a hallmark of adaptable cloud-native services. Now we define the inference response record. Similar to inference request, it uses JSON property name for clear JSON serialization. The result property, line 49, holds the AI model's output. Notice request ID, line 51, is also part of the response. This is crucial for linking requests to their corresponding responses, maintaining that critical traceability we discussed earlier. It allows clients to match asynchronous responses with their original requests, which is common in high-throughput AI inference scenarios. The inference response also includes processing time ms, line 54, and model version, line 57. Processing time ms provides immediate feedback on inference latency, which is a key performance indicator for AI services. Model version is vital for managing AI models in production. In a cloud-native environment, you often have multiple versions of a model deployed simultaneously, e.g., for A/B testing or canary deployments. Including the version in the response allows clients or downstream services to understand exactly which model generated the output, aiding in debugging, auditing, and performance analysis. This supports robust model lifecycle management. We move into the Abstractions section with the iModel Executor interface. This is a powerful architectural pattern, defining a contract that concrete implementations must adhere to. The primary benefit here is decoupling. Our service doesn't care how the AI inference is performed, only that it can be performed via the execute async method. This allows us to swap out different AI runtimes, e.g., ONNX, TensorFlow, PyTorch, or even a call to a remote inference API, without modifying the core service logic. This flexibility is paramount in cloud-native applications, enabling easier upgrades, experimentation, and technology migration without disrupting the entire system. Here we introduce Mock Transformer Model Executor, a concrete implementation of iModel Executor. As the name suggests, it's a mock, designed for demonstration and testing. In a real-world containerized AI service, this class would be responsible for loading the actual AI model file, e.g., an ONNX file, a TensorFlow saved model, or a PyTorch trace, and interacting with a specific runtime engine to perform the inference. The fact that we have a mock highlights the value of the iModel Executor interface. We can develop and test the service logic independently of the complex, often resource-intensive, model loading and execution details. The Mock Transformer Model Executor constructor, lines 85 to 89, takes an iLogger and iOptions model config. The iLogger is injected for structured logging, a critical practice in microservices for observability and debugging. iOptions model config is how we access configuration data. By injecting iOptions.t, we leverage ASP.NET Core's configuration system, allowing model-specific settings, like name, version, or batch size, to be externalized. This is a core cloud-native pattern. Configuration should be externalized from the application code, making containers portable and configurable at deployment time without rebuilding the image. The execute async method, lines 90 to 97, is where the mock inference logic lives. The first thing it does is call ensure model loaded. This is important because loading a large AI model into memory can be a time-consuming and resource-intensive operation. By loading it once and then reusing it, we optimize performance and reduce memory churn. In a container, this means the model is loaded when the container starts or on the first request, and then remains resident. This singleton pattern for model loading is common to avoid redundant loading and ensure efficient resource utilization within the container. Inside execute async, we use a stopwatch, line 98, to measure the simulated inference time. This is a practical detail for performance monitoring. We then log the incoming request, lines 100 to 101, which is crucial for debugging and understanding service activity. The task, delay, line 104, simulates the actual computation time of an AI model. The delay is made proportional to the prompt length, which is a simple heuristic to mimic how real AI models' processing times often scale with input size. This helps in making the mock more realistic for testing performance characteristics. After the simulated delay, the stopwatch is stopped, line 106. A mock result string is generated, lines 109 to 110, incorporating the _config, name and _config, version to demonstrate that configuration values are being used. We then log the completion of the request, lines 112 to 113, including the request ID and elapsed milliseconds. This detailed logging is invaluable in a production cloud environment for tracking individual request performance, identifying bottlenecks, and debugging issues across distributed services. Finally, execute async constructs and returns an inference response, lines 114 to 120. It populates the result, request ID, processing time ms, and model version fields. Returning a complete response object ensures that all relevant metadata about the inference is available to the client. This includes the unique request ID for traceability, the actual processing time for performance analysis, and the model version for reproducibility and auditing. This comprehensive response structure is a good practice for any API, especially for AI services where model lineage and performance metrics are critical. The ensure model loaded method, lines 123 to 134, implements a lazy loading pattern for the AI model. The _is model loaded flag ensures that the model loading logic, simulated by thread, sleep, 500, runs only once. This is a critical optimization for AI microservices. Loading large models can consume significant memory and CPU, and doing it on every request would be prohibitively expensive. By loading it once, typically on the first request or service startup, we ensure efficient resource utilization within the container. This also aligns with the singleton registration of iModel Executor later, implying that a single instance of the model executor, and thus the loaded model, will serve all requests. We move to the configuration section, starting with model config. This class defines properties for model-specific settings like name, version, and max batch size. Separating configuration into dedicated classes like this, and binding them to specific sections in app-settings.json, is a standard and robust pattern in ASP.NET Core. This allows us to externalize configuration, making our microservice more flexible. In a containerized environment, these values can be overridden via environment variables or Kubernetes config maps, enabling dynamic adjustments without rebuilding the container image. This is a cornerstone of cloud-native design for operational agility. Similarly, service config defines configuration specific to the service itself, such as the port it listens on. Just like model config, externalizing this setting is vital. Hard-coding the port would make the service difficult to deploy in different environments or alongside other services on the same host. By making it configurable, we adhere to the 12-factor app principle of config, strictly separating configuration from code. This flexibility is essential for deploying services efficiently in container orchestration platforms like Kubernetes, where ports might need to be dynamically assigned or mapped. Now we transition to the HTTP API layer with Inference API Handler. This class is responsible for handling incoming HTTP requests, parsing them, delegating to the iModel executor, and formatting the response. The comment notes that in a production setting, this would typically be an ASP.NET Core controller or minimal API endpoint. For this example, we're using a more basic HTTP listener setup, but the architectural role of this handler remains the same. It's the entry point for external communication, acting as the front door for our AI inference microservice. The Inference API Handler constructor, lines 161 to 164, takes iModel Executor and iLogger via dependency injection. This is a classic example of the dependency inversion principle and inversion of control. The handler doesn't create the model executor, it receives it. This makes the handler highly testable. We can inject a mock executor, and decouples it from the specific implementation details of AI inference. The logger, as always, is crucial for observability, providing insights into the API's operation and any issues that arise during request processing. The handle request async method, lines 166 to 176, starts by validating the incoming HTTP request. It checks for the correct HTTP method, post, and the expected path, /infer. If these conditions aren't met, it returns a 404 not found response. This early validation is important for efficiency, preventing unnecessary processing for malformed or irrelevant requests. It also defines the public contract of our API endpoint, clearly stating what kind of requests it expects. This is a basic but essential part of building a robust web API. Next, handle request async proceeds to read the request body, line 179, and deserialize it into an inference request object using system, text, JSON, line 180. This is where the JSON payload from the client is transformed into our internal C# data model. It then performs basic validation on the deserialized request, lines 182 to 186, checking if the request is null or if the prompt is missing. If validation fails, a 400 bad request is returned. Input validation is paramount for security and stability, preventing malformed data from crashing the service or exploiting vulnerabilities. It's a critical layer of defense in a public-facing API. After successful validation, the handler calls _model_executor.executeAsync, request, line 189, to perform the actual AI inference. This is the core business logic delegation. Once the inference response is received, it's serialized back into JSON, line 191, ensuring pretty printing with right indented equals true for readability, useful in development, though often omitted in production for performance. Finally, the response headers are set, content type, status code, and the JSON payload is written to the output stream. This completes the request-response cycle, delivering the AI model's output back to the client. The try-catch finally block, lines 198 to 209, is crucial for error handling. Any exceptions during request processing are caught, logged, _logger.log error, line 200, and result in a 500 internal server error response. Logging the exception details is vital for debugging in a production environment. The finally block ensures context, response, close, is called line 207, which is necessary to properly terminate the HTTP connection and free up resources. Robust error handling is non-negotiable for cloud-native services, as it ensures resilience and provides clear feedback to clients and operators when things go wrong. We now enter the Hosting Infrastructure section with Inference Hosted Service. This class implements iHosted Service, which is a key ASP.NET Core abstraction for managing long-running background tasks or services within the application's lifecycle. In our case, this service is responsible for starting and stopping the HTTP listener that serves our AI Inference API. This pattern allows our web server logic to be cleanly integrated with the application's dependency injection and lifecycle management, rather than being a standalone, separate process. It's how ASP.NET Core applications host web servers like Kestrel, but here we're using HTTP Listener for simplicity. The Inference Hosted Service declares several private fields, _listener, the core HTTP server, _handler, to process requests, _logger, _config, for service settings, _listening task, to hold the background listening task, and _CTS, a cancellation token source for graceful shutdown. These fields represent the essential components needed to run and manage our HTTP server within the hosted service pattern. The cancellation token source is particularly important for cloud-native applications, enabling graceful shutdown when a container is being terminated, preventing abrupt request drops and ensuring data integrity. The constructor for Inference Hosted Service, lines 226 to 236, injects the Inference API handler, iLogger, and iOptions service config. It then initializes the HTTP listener and sets up its prefixes. The HTTP listener is a low-level HTTP server provided by .NET. The comment at lines 232 to 235 is crucial. HTTP listener has specific requirements for URL ACL setup on Windows or sudo/ capabilities on Linux/ macOS. This highlights a practical consideration for containerization. While HTTP Listener is simple for demos, in production, Kestrel, ASP.NET Core's default web server, is generally preferred as it handles these complexities more gracefully and is optimized for cloud environments. The start async method, lines 238 to 243, is called by the ASP.NET Core host when the application starts. It initializes the cancellation token source for managing the service's lifetime, starts the _listener, and logs that the service has begun listening on the configured port. Logging the startup information is critical for operational visibility, confirming that the service has initialized correctly within its container. This is the point where a microservice becomes available to receive network traffic. Inside start async, we launch a background task, _listening task, using task, run, lines 245 to 252. This task contains the main loop for accepting incoming HTTP connections. The while _CTS token.is cancellation requested condition ensures that the loop continues until a cancellation is requested, enabling graceful shutdown. The _listener.get context async asynchronously waits for a new request, which is a non-blocking operation, essential for maintaining responsiveness in a server application. Once a context is received, line 251, we use _task, run, =handler.handle request async, context, _CTS, token, line 256, to handle each request in a separate, fire and forget task. This allows the listener to immediately go back to waiting for new connections, preventing a single slow request from blocking the entire server. The comment at lines 254 to 255 is very important for cloud-native AI. In production, you typically use a semaphore slim or a messaging queue, like channels, to limit the number of concurrent requests. This prevents the container from being overwhelmed, leading to out-of-memory, OOM, errors, especially with memory-intensive AI models. Without such throttling, a sudden traffic spike could easily crash the container, impacting reliability and availability. The catch blocks within the listening loop, lines 262 to 267, handle potential exceptions. Specifically, it catches HTTP listener exception when cancellation is requested, line 262, which is an expected scenario during shutdown. Any other exceptions are logged, line 265, ensuring that runtime issues are captured for debugging. Robust error handling in this critical listening loop is essential for the stability and resilience of the microservice, preventing a single error from crashing the entire server and ensuring that operational teams have visibility into problems. The stop async method, lines 271 to 280, is called by the host when the application is shutting down. It logs the stopping message, cancels the cancellation token source, stops the HTTP listener, and then closes it. Crucially, it awaits _listening task, line 279. This ensures that the background task responsible for accepting connections has a chance to complete gracefully before the application fully exits. This graceful shutdown is vital in cloud-native environments to prevent in-flight requests from being abruptly terminated, which can lead to data inconsistencies or poor client experiences. It's a key aspect of building resilient microservices. We arrive at the program class, which contains the main method, the entry point of our application. This is where the ASP.NET Core host is configured and built. The async task main signature indicates that the main application thread can perform asynchronous operations, which is common in modern .NET applications, especially for I/O bound tasks like starting a web server. This setup is standard for any ASP.NET Core application, providing a robust foundation for our microservice. The main method begins by creating a host using host.createDefaultBuilder, args. This builder provides sensible defaults for logging, configuration, and dependency injection. We then configure the application settings using configure_app_configuration. The add.json file, appsettings.json, line 294, instructs the host to load configuration from appsettings.json. The comment wisely points out that in a container, this appsettings.json might be mounted as a Kubernetes config map, allowing deployment-specific settings to be injected without modifying the container image. This externalization of configuration is a fundamental cloud-native pattern. Inside configure services, we use services, configure t, context, configuration.getSection, section name, lines 299 to 300, to bind specific sections of our configuration, like model and service, to our strongly typed model config and service config classes. This pattern is incredibly powerful for managing configuration. It provides type safety and compile time checks, making it less error-prone than accessing configuration values directly by string keys. This further reinforces the cloud-native principle of externalized and well-structured configuration. Here, we register our core dependencies with the dependency injection container. Services.add_singleton iModel Executor, mock transformer model executor, line 303, registers our mock AI model executor as a singleton. This means only one instance of mock transformer model executor will be created throughout the application's lifetime. This is a critical design choice for AI inference services. AI models are often very large, hundreds of MBs to several GBs, and expensive to load. Keeping a single instance in memory optimizes resource usage within the container, preventing multiple copies of the model from consuming excessive RAM. If this were add-scoped or add-transient, each request or consumer could potentially trigger a new model load, leading to OOM errors in a high concurrency scenario. Services.add_singleton inference API handler, line 304, also registers the API handler as a singleton, which is appropriate since it's stateless and can handle multiple requests concurrently. We register our inference hosted service using services.add_hosted_service inference hosted service, line 307. This tells the ASP.NET Core host that this class should be managed as a background service. The host will automatically call its startAsync and stopAsync methods during application startup and shutdown, respectively. This pattern cleanly integrates our HTTP server with the application's lifecycle, ensuring it starts correctly and shuts down gracefully. It's a fundamental part of building robust, long-running services in .NET Core that can be reliably deployed to containers. The configure logging section, lines 308 to 313, sets up our application's logging. We clear providers, to remove default providers and then add console, to ensure logs are written to the console. Set minimum level, log level information, configures the verbosity. For cloud-native applications, logging to the console, /stare, is the preferred method. Container orchestration platforms like Kubernetes typically capture these console logs and forward them to a centralized logging system, e.g., Elasticsearch, Splunk, Loki. This makes logs easily accessible for monitoring, debugging, and auditing without requiring special file system mounts or agents within the container. Finally, build creates the configured iHost instance, line 315, and await host.runAsync, starts the application, line 318. This method blocks until the application is gracefully shut down, e.g., via Control+C or a SIGDEM signal from a container orchestrator. When runAsync is called, all registered iHosted service instances, like our inference hosted service, will have their startAsync methods invoked. This is the culmination of all our setup, bringing our AI inference microservice to life and making it ready to serve requests within its containerized environment. Thank you for your attention. This lesson is excerpted from Volume 7, Chapter 11 of the C# and AI Masterclass ebook series and from the volume Cloud Native AI and Microservices, Containerizing Agents and Scaling Inference. You can find all the details here, https://github.com/edgarmilvas/C# programming series. The ebook also includes diagrams, advanced examples, and 5 exercises with solutions for every chapter. There are 26 chapters. If printed, it would exceed 600 pages. Subscribe to the channel to watch more videos. I look forward to seeing you in the next lesson.